Hello, James Sylvester from JPS Reliability and also the Reliability Training Institute RMS. And what we're going through today is case study 5. This is the final of the case studies we're presenting of the first batch. As with the previous 4 case studies, what we're trying to link up is a failure cause, a failure mechanism, and a failure mode, so we can actually eliminate these defects from happening again. We're going to be using the Meraki Academy Science. So this is where we get the theory, the mechanics, the physics of the bearing, and we try and link it up with what we're doing practically in our reality. We've got a few previous case studies which you can view. The previous case studies are found on the RMS website. And the first one was an electrical motor termination connection defect. This was a good case study that highlighted you need to use other technologies like infrared thermal imaging. Case study 2 was a supply fan defect. Again, this case study showed us storage of spare units, spare standby fans, and also making sure things are installed correctly. Case study 3 was the electrical defect or IVI card defect. This was where vibration analysis was actually an indicator of a failure, not a predictor of a failure. Number 4 was a vibrating screen gearbox. Again, another great case study. This one was showing us that if you use the correct sampling, the correct techniques, you can measure an in-race defect even in the harshest environments of a shaking screen. And today's case study is number 5, which is on a 4-point contact bearing, which rotates at 23 RPM, and that the failure was detected before the functionability of the system was affected. These case studies are all featured in my book, Enhancing Reliability Through Vibration Technology. A video of the book overview is found on the RMS website and details how you can get it there as well. So this is the slurry pot here. It's about 1.5 meters diameter, about 2 meters high, full of slurry, and it's mixing a product at the start of a process. There's a floor or a cable coming up. This is the transducer mounted on the outside of the bearing here, and that's a grease line. You can see here at the input to the grease line a lot of suspected grease coming out. Transducer we used on here was a very good quality 100 millivolt G, because you can get 100 millivolt G and you can get a good quality 100 millivolt G. And it, again, with a high powerful curved magnet, so we got good surface contact. The history was we often come to the site to help out with other things, and they noted that they are starting to get a batch of these slurry pots failing. It wasn't the cost of a bearing, it was more the interruption to the just-in-time process. So if this did fail during a batch run, let alone financial cost of losing a batch, it's a knock-on effect of the just-in-time for the next process for machining to keep going to the final product. And there's lots of costs involved, not just the bearing. So them to have a lot of pre-warning that a bearing was going to fail, they can then schedule it around production needs and reduce the damage to the company financially. This is the 4-point contact bearing, so you can have the outer and inner race can rotate. These marks here are actually part of the manufacturing process. It wasn't damaged from the bearing. On this particular case, we have the slurry bolted to the middle, and the outer race is stationary and it rotates. There was lots of doubting Thomases on whether we can actually pick up a defect with vibration analysis because it's going so slow. But the high where we're sampling, you're getting sort of into the ultrasonic range anyway, getting up that high. This was our first data. So we chose peak view and we were using the time waveform, and we were sampling really high. We played with different types of filters and bandpass filters, and we decided on one which we thought and we could see we'd get the best data from. This one here, which is the same scale, is one slurry pot bearing, and this is another slurry pot bearing. Straight away, you can imagine this going ting, 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 ting. You can imagine the bearing sort of something not right in that bearing, so it's pinging away, and it's not great. And it was near enough periodic sort of impacting. So we ran the FFT on that waveform, and we got this. I mean, we don't worry about levels, we're looking at patterns and waveform analysis, and on the FFT, even though it's 0.0105, we could see we had a peak and some mounds, and these mounds were sidebanded by rotational speed, and the peak was at 24.51 orders, and that's the inner race defect frequency with a rotating inner race on this particular bearing. So we are confident we've got an inner race defect. What we weren't too sure about is what stage of failure it was, because the levels were really low. But given the high risk of it, and they didn't want no unplanned breakdowns, took a bit of convincing, but they did take the bearing out. And when they took it out, they said it still rotates, nothing wrong with it. And that's what we found when we split it open. So we cut it open. This isn't being cleaned, this is straight out. Look at the nice contaminant and all the crappy grease there. You can see here, the cage pocket has been broke for so long, it's all been overrolled like a stone in the ocean. It's all getting smooth. And here, different failures of cage pockets. Looking closer, we can actually find some cage pockets which were good, some which had some slight cracks in it, and some totally failed. And here you can see there's one there. And the grease had lots of overroll metal particles. It felt really, really bad. Cleaning up the bearing, and there was our inner race as we expected. Some lovely craters all along here, and it was more part one of the bearing, one small section of the bearing would have gone more than the rest. You can see here the cracks are spawning, so this is like it's got overroll or just subsurface fatigue, and it's cracked and coming and starting to peel up. There's some damage to the outer race, but a lot higher damage to the inner race. This is a rolling element, and it's all pitted and rolled over. So this is a really good find. And now we know at a certain level in the time waveform of a certain pattern, we know the bearing is failed. As to how long this bearing would have lasted, it's one of those where it's at such a high risk that it could catastrophically fail, that it is a good call to pull out. As with anything, you must do commissioning of new bearings. So we commissioned a new bearing after it was changed, and if you can see down the bottom here, there's a little blue line. Well, that is the time waveform trace of the new bearing. So the new bearing is so smooth, whereas this was the defect bearing. One thing we did notice on the bearing, which we thought was quite a cause of failure, is that on the first image you saw the grease pipe coming in and lots of grease coming out. The bearing's about that diameter. There's only one input for the bearing for grease. Even though there's a few holes around it you could pipe around, they were putting the grease into one point. And it was one point of the bearing had the higher damage on the inner and outer race, and that's opposite the greasing point. So it was as if the grease, when it is greased, would come out and couldn't totally replenish around the opposite side. And after 5 years of all the overall and the stress of the dynamics of it moving and the weight, it just spoiled and failed. And perhaps if they had more grease points around it, they may double their life and actually reach 10 years. So when we try and look at with the science, so the failure cause lack of lubrication. But why? But due to an ineffective lubrication system. So on the one part of the bearing, the lube wasn't refreshing enough, wasn't getting around there, even though it is all coming out at the input. The mechanism of failure was that due to the lack of lubrication, the insufficient system, that is getting additional stress load on the bearing raceways. And we detected it through vibration analysis, and it is a bearing spooling. So you can sort of say it's a design flaw, but is it a design flaw? Because it did reach the 5 years, but it can be improved. That's what we want to do when we find failures, is work out why they happened and how we can improve it. So we think the lubrication was getting all the way around the bearing, and an easy way to rectify that was get a new copper pipe in, pull it around to the back. So when it's greasing at the 4 points and greases coming in equally and going to all of the bearing. This defect was detected and production losses were avoided. So we avoided a negative functionability event. So everything could still function, the system could still function, and it did what it said, and they could schedule in a bearing change without negatively affecting the system. So in this case, the vibration analysis was it was an indicator, and it would have been a predictor if we had trending, because you could have trended it, and as that damage got worse and worse, the peak waveform would have gone up and up and up. And now we know at what level that bearing is really bad. We can use vibration analysis, condition monitoring tool as a predictor for the health of the system. So as before, a little slide on how we can help you upscaling. So we're very passionate about training and improving reliability and helping people use the condition monitoring tools the best. So we do upskilling and practical training and mentoring, traditional reliability services to support you, and training with the Mobius tools, and that's conforming to ISO 18436, and we can do either MyBook or BINT certification. Again, slide in here again, a great slide which shows that we don't just use vibration analysis or lubrication or ultrasound. We use them all. Each particular technique for a particular failure, a particular application, can be an indicator. So it can indicate it's failed before the system functionally fails, or it can be a predictor. In this case, it was an indicator, because and we can predict now, we know what level is, and we can now trend it. Also, it shows you ultrasound would have been just as amazing in this situation with a high sample rate and the ultrasound waveform, and it probably been even clearer. This is a little bit about JPS. I shan't stay on too long, but it's the same as the past 4 slides. And again, the murky science, where we're linking the reality and the theory together, has been really, really beneficial. So thank you very much. That was a final case study of 5. Hopefully you've enjoyed the previous 4 as well. And chatting to the RMS reliability training team, we're actually going to do a 6th bonus one. This one is actually on a case study which took over 2 years on a dynamic vibration absorber. That'll be coming up next week, so keep an eye out for that. It'll be a bit longer, it's a lot more to talk about, but it'll be really interesting, and hope you see it then. Thank you.